Well, good morning or good afternoon, everybody. This is Mr. Kinney. We're going to be going over part 3 of our notes on thermochemistry. So let me get this off of here. Just want to do a reminder for you. So thermochemistry, this is the chemistry of energy, how energy moves and flows in and out of systems. Now that's a big deal here. So when I'm going to zoom out, actually I'll just scoot this over. So just for a reminder for you, when it comes to thermodynamics, we need to define what the system is and the rest of the universe or the surroundings. And if energy is going, we're going to say now that the system is this flask. Okay, well, good. Look at it, it's even labeled right there. Now this is meaning that any energy we put into this is going to be positive energy because we're putting energy, we're adding energy into the system. Energy entering endothermic. If we remove energy from the system, if energy is exiting the system, that's going to be exothermic. And since we're removing energy, that's a negative operation, you're going to have a negative sign. Now, when we are working with a lot of our calculations, notably Q, energy, or heat, heat energy is Q, equals the mass times the specific heat times the delta T. The delta T is where we're going to end up getting either the positive or negative sign, and that'll tell us, are we adding heat to the system or are we taking heat away? So we have come up in this unit up to this point. Now what we're going to do is we're going to take a look. I'd like you to look at this graph. We're going to create this graph, and I think you have this in your packet under your table of contents. So if you wanted to get this out to kind of help you out, you're welcome to do that. I'd encourage it. So this graph represents, we have, let's say, water that is frozen. It is over here at really cold temperature. And let's say this is like, okay, so anyway, so we're going to add, let's say this is ice. So we add heat to the ice. Now the ice is still frozen. It's still a solid, but it's not as cold. And then when it gets to its melting point, if we're, at this point here, what happens is the ice begins to melt. Now, while it's melting, here's the interesting thing. If you have a cup of ice water, it is going to stay at 0 degrees Celsius inside of there because that's the freezing point, melting point of ice. And so as long as you have ice in that cup inside of there, it's going to stay exactly at 0 degrees. Once the last bit of ice is melted away, now the temperature begins to increase. Now it begins to warm up. And it'll continue to warm if it's water until you get to the boiling point of water, which is the vaporization point. Fancy word there, vaporization, boiling. Once water gets to 100 degrees Celsius and begins to boil, it is going to stay at 100 degrees. Now, as it boils off, steam will be released, which is the gaseous phase. Now, the steam, you can see here, its temperature is increasing. Steam can get incredibly hot. So if you can stick a thermometer into boiling water, it'll be 100 degrees Celsius. If you raise it up a little bit into just where the steam is, you might have a little bit higher than 100 degrees because steam has to exist higher than 100 degrees Celsius. Now, what's with all this? On this graph, any place we have these little angles right here, we have a delta T. We have a change in temperature, and that's where we use Q equals MC delta T. We can use this equation when a solid is warming up or cooling down, when a liquid is warming up or cooling down, or when steam is getting hotter or cooling down. But what about in this point right here? These two parts where we have the ice-water mixture when the temperature does not change. And if you use Q equals MC delta T, the delta T will be 0. And look at, if you're frying some ice, okay, you put ice in your frying pan, you're adding heat to that thing, okay? And if you say, well, wait, there's no temperature change, therefore there's no heat being added, well, we have to use another equation that does not have the delta T in it. And that's called, it's going to be called heat of fusion or heat of vaporization. So there's a little intro. You didn't have to write anything. I hope you didn't write any of this down. We're going to get started on our notes. So to begin with, I'm thinking that our notes, I'm going to start the notes. Let's see, we started, let me zoom out here a little bit. This was our notes more or less that we started with. We introduced thermochem. We talked about the surroundings. We did the mousetrap activity. We said plus is adding energy endothermic, negative is energy exiting the system exothermic. Then part 2 of our notes, it was the big notes day, sorry about that, but we were talking about all the factors that go into the heat equation. Heat, the symbol is Q, the units are calories or joules, or it could be big C or little c calories. We've got the specific heat, okay, and the symbol for specific heat is CP, or just C, and I gave you this chart that shows the specific heats for different materials, so you should have that in there. We've got delta T, the final minus the starting temperature. We've got the mass. Then I may or may not have, we came to this part, Roman numeral 4. So take a look. If we didn't get to Roman numeral 4, I think one of my classes I didn't. So Roman numeral 4, calculating heat. So calculating heat, and we're just going to write A, and this is Q equals MC delta T. Now for my substitute, if you need to pause this a moment, if the class didn't get this one, hit the enter button. And okay, I'm going to continue on now. So when we have a change in temperature, this is our equation. Okay, we got heat here. So this is when we have a delta T, a change in temperature, we can use this equation. Now there's going to be some time, like I talked about, where we can't. So now we're going to go to part B right here. Okay, so now I'm going to start on a fresh sheet of paper here. Let me zoom out so we can see. So part B. So we're still under Roman numeral 4, which should have been, what we call calculating heat. And I'm just going to say calculating Q because I'm going to use the appropriate symbols here. Let me zoom in so you can see that better. So A was Q equals MC delta T. Now we're on B. So this is what we do. How do we figure heat, Q, when there is no delta T? When no change in temperature. How do we do that? Well, let's see. So how do you calculate? Now, so what this comes down to, when there is no delta T, this is called a phase change, P-H-A-S-E. This is a phase change. When we are going from, let's say, we are going from, we'll use water. We're going from ice changing into water. During that process, until all of the ice is melted, that is a phase change. We're going from a solid to a liquid. Okay, and there's no temperature change there. If it's water, it's going to stay, this will be 0 degrees Celsius. 0 degrees Celsius. It can also be, the other phase change can be when say the water begins to change into steam. Now the fancy term here is going to be a liquid, when the liquid changes into a vapor. So kind of a new term for us. You've heard of that. Evaporation is a type of vaporization. But when something steams, it's vaporizing. And with water, that's 100 degrees Celsius. So while the water is in the process, you have that pan of water on your stove. You're heating it up. The whole time, as long as there's water in that pan, it's going to stay at 100 degrees Celsius. There's no delta T. So what we use is, we use a different function. Okay, we're going to use what's called either heat of fusion or heat of vaporization equation. So let me get back this so you can see a little bit of all that. So first off, let's see, what do we got? Q, there's a new Q for us. Q can equal the mass. Okay, nothing new. But now we're going to use something that's called delta H, that's for heat, of fusion. Now, the fusion, I look at that F and I think, hey, freezing. Okay, that's going to be this process here. That's when you have ice changing to water, or the opposite. I'm going to put an opposite arrow. If we've got water, okay, so water changing to ice, that's freezing. If you have an unfreezing, we use heat of fusion, which we call this delta H of fusion. Okay, so there we go. And I'm just going to put here, this is for freezing. F-R-E-Z, oh, but another E, freeze or melting. Now, whether it's freezing or melting, it'll be a positive or negative number. If we're freezing, we're removing heat energy, right? So we're removing energy from the system. That will be a negative heat of fusion. If we're adding heat to something and it's melting, okay, we're making it melt, we're adding heat to it, that's going to be a positive heat of fusion. Let's see, the other one we've got is, let's see, so come over here and let me see, got all that, liquid, yeah, I got that. So we've got melting. Let's talk about if we've got melting occurring. Okay, so obviously that's solid changing to a liquid. The other, okay, so we got that there, or we've got freezing going on here. Okay, and the freezing would be a liquid changing to a solid. Oop, that should be a Q there. Okay, so in this process here, we are, if we're going from a solid like ice to a liquid, we're adding heat to it. That's going to be, I'm going to scoot this over, endothermic. Endothermic. Because energy is entering the system, making the solid melt into a liquid. The other way around, if we've got a liquid like water and we're making it turn into ice, we've got to be removing heat energy. So energy is exiting the system. That's going to be exothermic. So this is where it kind of feels weird. We've taught with chemical reactions, if it feels cold, it's endothermic. But in this case, it's going to be kind of, when something is freezing, if it's a phase change, it's actually going to be exothermic. Now, we got another one we're going to be using. Oh, let's see. It's going to be heat of vaporization. Oh, I should have written it over. Okay, I'll just squeeze it in here. Q can also equal mass times delta H of vaporization. I'm just going to write vapor. I'm not going to write the whole term of vaporization. So let me see, this is almost like a little data table I've made here. So if we got exothermic happening, this is going to be now, if we've got this liquid right here, if we've got a liquid changing into a gas, okay, I'm going to say a vapor, gas, I'll just put, now when we say gas, we don't mean gasoline, we mean a gaseous material. Okay, this process is called vaporizing. You might be more comfortable calling it boiling. So let's see here. I'm going to draw a line this way. Melting and vaporizing. We're adding energy into the system, so it's endothermic. Exothermic. We got liquid changing to a solid, or what we can also have, the other next process is when a gas or a vapor, like steam, changes back into a liquid, like water. That process is called condensation. You see that, especially in the summertime, you get a nice cold cup of soda or something like that, or a nice drink, you got ice in there, and pretty soon you're going to see little water droplets forming on the outside. That's condensation. So let's see here. So we've got, that's an exothermic process. And with this, I'm going to put it off to the side here. We have a plus value of Q. If we are exothermic, if we have energy is leaving the system, that's going to be a negative value for Q. Okay, it's getting colder, it's getting hotter there. So let me zoom out so we can kind of take a look at that. If the sub needs to pause that for you, I know there's a bit, we can do that. But then we're almost done. We're just going to draw. Okay, here's my finished one. We're going to go through and draw this. And I don't want you just to say, I'm just going to use the copy you gave me, or no, I want you to draw it out. I want you to go through that process. So I'm thinking, let me zoom out here. Take a lot of room. You should have, if you're at the bottom of the page, let's start again. And let's get this graph set up. I'm going to use quite a few lines like this. And I'm going to come over, setting the X and Y axis for this graph. Thicken that up a little bit. Okay, and let's label this graph. We're going to label down here, let's make this one -10 degrees, and this will be temperature over here, degrees Celsius. I'm going to go up a couple of lines and say this is 0 degrees. Now this isn't to scale. I'm just going to zip up. I'm going to go about 3 lines up and label this 100 degrees Celsius. And then up here, I'm just going to say, okay, this is 500 degrees plus, okay, up there at the top. So we've got a graph setting up. Now across here, this is going to be heat energy, or Q for short, if you got that down. Over here is going to be low Q, or low energy. Over here is going to be high Q, or high energy, if you like. Abbreviate energy with the E's. So the first thing we're going to do, let's start right down here in the corner. Let's say we're working with ice. Okay? Let's label this chart of H2O. Okay, we'll call it chart of H2O. So we're going to start here, and let's just draw a nice little 45-degree line, roughly, something like that. We're going to label this ice, because we're at between 0 and -10 degrees. If we have water, it is going to be frozen. Let me zoom in some more. And so now what can happen is you ever taken ice out of the fridge right away, stick it to your tongue, and it kind of sticks on your tongue? Okay, but then a couple minutes later you try that, it doesn't do it? That's because when it first comes out of the fridge, for the freezer, it's really cold and it'll freeze instantly to the water on your tongue. Later on, when it's around here, it's not quite that cold. Anyway, so let's now draw. So we get some ice out. It starts to, you take it out of the freezer, it's starting to cool down. It's not melting yet. Then it gets to the point of the freezing point of water. And now the temperature, now this is temperature, it's getting warmer, warmer, warmer. Now it stops changing its temperature. We're still adding heat, okay? It's getting heat from the surroundings. And so what happens here, let's label this melting. And I'm going to draw an arrow that way, saying this is the way we're going right now. And we're melting. Now at this point, there is no delta T. You cannot use MCAT right there. Now let's add some more energy. At some point, once this water, I'll make this a little bit longer. At some point, once the last bit of the ice is melted, and now you have nothing but water in the container, now the temperature begins to increase. And we're going to draw a line right up to that 100-degree mark right there. So at this point, the ice has become water. Okay, and we do definitely have right here, we have a delta T. Yay, we have a change in temperature. And you would have to use Q equals MC delta T there to figure out equations for that, and Q for that. All right, let's continue on now. Now the water gets to the point now, when it gets to 100 degrees, it begins to turn into a gas. And now the temperature is going to flatline again. So we'll draw this maybe a little bit longer because we need to write this process. We got ice, it's melting, we got water. The process, what do you call the process when water changes to a gas? Okay, if you said boil or vaporize, cool. I'll put vaporize. If you like, we can put boil. So it begins to vaporize. And I'm going to put an arrow here saying this is the direction that we're moving here. There is no delta T here. We cannot use MCAT right there to solve any problems. We need to use the heat of fusion equations. Now let's say now at some point when the last molecule of water has boiled out of whatever pan you're working on, now the temperature of the steam, this is going to be steam over here. Make sure I'm not off the page. Steam. It's getting really high. We do have a delta T here, so you can use Q equals MC delta T. Actually, I'm going to come back down here. We have a delta T there as well. Whoops, not an A, delta T. So any place where this graph is slanted, we can use delta T because we have a change in temperature. Now this part right here, since this is the freezing, you have to use Q equals the mass, so you need to know how much you have, times delta H, and I'm just going to go F for fusion. Okay, that was right up there. That's just how we abbreviate it. So right here, since there is no delta T, this is the equation you'd need to use. And all you have to do is know how much of the water or ice you have, and then you just need to look up on a chart what's the heat of fusion. And guess what? Ta-da! Here's your lovely periodic table, and look at right there, latent heat of fusion of water. We have 80 calories per gram or 334 joules per gram. We also have the heat of vaporization of water, 540 calories per gram, so and to 2260 joules. And what this means, the heat of vaporization, it says that you would need to add 540 calories of energy to 1 gram of water to change it into steam. So for every gram of water, it's going to take 540 calories to change it into steam. If you're going to freeze water, you need to remove 80 calories for every gram of water to make it freeze. Or if you're melting water, it's the other way. It'd be plus 80. So that's what this means. These numbers tell you how many calories you would need to either add or take away to make it freeze. Oh, you might put on your periodic tables fusion, that would be freeze or melt. If you're freezing, you're removing energy, you need to use a negative 80. If you were melting, you're adding energy, that would be plus 80. And that's how those work. Heat of vaporization, okay, that's going to be if you are condensing, or if you're vaporizing. If you're vaporizing, you're adding heat, you'll use the plus value, plus 540. If you were condensing, if you were cooling it down, you would use negative 540. And that's how that works on those. But let's finish our graph here. So let's see. If we are going in this direction, we're adding heat energy. Adding energy going this way. That is going to be endothermic. This side over here, if we're going in this direction, okay, let me draw an arrow up there. Okay, that's going to, you're losing energy. Losing energy. It's going to be exothermic, because energy is exiting the system. So if we're starting up here with steam, so the process of steam changing into water, this is called, we're going to draw an arrow this way, this is condensing. When steam is changing to water, condense. Then it's water, and then as the water begins to freeze, we call that, yep, you got it, freeze. Finally, a word in science that we don't have to, we know what it means. So, in that direct fact, what I'm going to do is, oh, I think I won't do that. So let me see, I think we got everything done here. Just about. So, oh yeah, this part of the equation, since we have no delta T here, we need to use in here, how will I do that? I'll put, let's put, I'm just going to squeeze it in there. Q equals mass times delta H of vaporization. Oh, you're going to be really mad at me. So tell you what, I'll just, if you need to, let's just draw an arrow right there if you need to. Q, if you're calculating heat, you need to know the mass, and then you're going to multiply it by the delta heat of vaporization. Okay, so I know you're kind of right now going, okay, I got it, sorry about that. But we're going to do some practice problems now. So if you need to, the sub can pause this for a moment. But I'm going to have you get out your packets. Uh-oh, where are your packets? Here we go. Here's the packets. This is the packet there. Okay, let me find the packets naturally. Right there they are. Okay. So, in your packet, let's go to this page right here, the very first page in your packet. I'm going to have you work on these the rest of the period. So we've got a couple of equations on here for you. Here is Q equals mass times delta T times the specific heat. This is just MC delta T. Okay, you're used to that. And then down here, we're going to be, in this problem, looks like we'll just be using heat effusions, okay? So, and that's going to be Q equals the mass times delta H fusion here, okay? So when you go to set up these problems, let's read through. I'm not going to, I think these are pretty straightforward. How many joules of heat, that's Q, remember that, are given off when 5 grams, that's our mass. Water cools from 75 to 25. So we're going from this, so that'll be temperature starting. This is our final temperature. Oh, and look at this, temperature F. We're cooling down. So it tells us what the specific heat of water is right there. So that's CP on that one. So with this one, we have everything we need. And because we do have a delta T, you're just going to use Q equals MC delta T to solve that one. Not a problem. Let's take a look at number 2. Let's annotate that together. How many calories are given? Okay, that's Q. How many calories are given off by the water in problem 1? Okay. Oh, all right. So they just want to know calories. So you just need to convert your answer from number 1 into calories. And you can either recalculate, you can redo the whole problem, Q equals MC delta T if you like, or you can just use the conversion factor that there's 1 calorie is 4.184. 1 calorie equals 4.184 joules. So you can either just convert your answer here using the conversion factor, or you can just reset up Q equals MC delta T and just use that instead. Let's take a look at number 3. Let's get this set up. How many joules, that's Q, does it take to melt 35 grams of ice? Okay. Now we're melting. Melting. Are we adding energy or taking away energy? Yeah, we're melting. We're adding energy. I'm just going to put a plus number there. Just a reminder. Okay, we're adding energy. This is our mass. And the ice is at 0 degrees. So now this is where there's no delta T. No delta T. So we need to, and they're telling us the heat of fusion right there, so they're giving us the information. So we're going to use Q equals mass times delta HF, heat of fusion. These are actually easier than MCAT, because now all you got to do is put the mass in there. Okay, so you put the mass in. They tell you what the heat of fusion is, but is it going to be positive or negative? Well, we're melting, we're adding energy to the system if we're melting, so it'll be plus 333. So you can work that one out. Let's take a look at number 4. How many calories are given off when 85 grams? Okay, calories, we're looking for Q. This is our mass. Steam is condensing. Okay, so steam is condensing to liquid water. There is no delta T, okay? This is when there's not going to be a change in temperature. Here's the heat of vaporization for water. They're giving us that. Now, if the steam is condensing, if we're going from steam to water, is it getting hotter or is it getting colder? Yeah, hopefully you said it's getting colder. And if it's getting colder, are you adding energy to the system or are you removing heat energy from the system? And hopefully you're like, hey, if we're removing heat energy, that's going to be negative. It's going to be a negative interaction. It's going to be exothermic because heat energy is exiting. So the heat of vaporization value, you need to make it a negative 539.4. Q equals mass times delta heat of vape. Okay, so you can get the rest of those. I'm going to call it a day here. Bye.